morning. Good morning. I hope everybody is doing good. Hello, hello. Let's do some math. All right. So let's see. We are in Unit 7 currently. We have learned integration by parts. We've learned like stuff with that, like tabular method. We've learned trig IDs, trig substitution. And now we're on to our next one, which is a couple days worth of notes. And it's on using partial fractions to help us integrate. Using partial fraction decomposition to help us integrate. And you've learned partial fraction decomposition in pre-cal, so it's going to be a little bit of a review of that and then how to integrate that. So it'll be fun. I got 6 problems here for like a little warm-up, and this is actually a great review of everything we've learned so far in this unit. So hopefully we can do these together, but some examples of each, like this would be like a trig substitution right there, number 1. Number 3 would be like a trig ID. This is actually just straight up U substitution. Number 4 would be integration by parts. You got another trig ID here, another integration by parts. So, you know, we've got a lot of good examples. I think number 4 would be a good tabular method. So I got them all filled out here. Welcome to pause the video or try these on your own. These notes are completed online, but again, hopefully we can do these together. Okay. So good quiz review coming up. So yeah. Okay, let's go ahead and jump to the lesson though. So we are learning about something called partial fractions in order to integrate rational functions. So the idea is that we're going to be integrating something like this, p of x over q of x, some rational function. And it's going to be some rational function that we can't just straight up integrate using our other techniques. Like we can't do integration by parts. We can't do u sub or trig substitution, something like that. Okay? So the idea is to be able to take this fraction, p of x over q of x, and to break it up into smaller fractions. And then those smaller fractions are going to be able to be integratable. Okay? Now, there's 2 types of fractions that you can run across in 2 different situations we need to look at. The first one, the main one we look at, is when we have a proper fraction. And when you think of the word proper, well, at least when I think of the word proper, I think of the way like it should be. It's the proper way. And when I think of a proper fraction, I think of where the denominator is bigger than the numerator. So it's like an actual fraction. So when the numerator is less than the denominator, or I guess if I'm using this terminology, when p of x would be less than q of x, like in degree and stuff like that. Okay. Then we can do partial fraction decomposition, and we're going to review that pretty well. The other type I could have is improper fractions. Okay. And it's the reverse, right? So if it's an improper fraction, the numerator is actually greater than the denominator. And whenever we have a numerator greater than the denominator, we always want to divide first, and then we want to integrate or do partial fraction decomposition. Okay, so we'll look at examples of each. The big plan here is that we're able to break the rational into smaller fractions. Okay? And this works if q of x, all right, if q of x, the denominator, can be factored into linear factors. Today is all about having linear factors. And we know what linear factors are from when we factored quadratics. It's whenever you have x minus a number, x minus another number. So like, for instance, x squared minus 2x plus 1. So like if I were to factor that, it has linear factors. It's x minus 1 and x minus 1. So that's what I mean by linear factors. So the idea is to get it to look like this. We can take this fraction and strip it apart to its linear factors decompositions. And again, we'll review how that works. Okay. All right, let's look at an example. Okay, let's look at an example. This is a fun one to start off with because we have to first decide is it proper or improper. So that's always the question I like to ask with these. Well, I guess really the first question I like to ask is, can you do any of your other methods? Usually at this point, the answer is no. If I was you, I would try u substitution with the top, but that's going to end up taking this from a power of 3 down to a power of 2, and it won't be able to substitute out with anything on the bottom. So I just don't think that's going to work. All right, but anyway, we're given a rational equation, right? It's definitely rational because we have something divided by something. Is it proper or improper? Well, you have a higher degree on top, so we're going to call this improper. And if it's improper, we want to divide first. So we are going to divide. Now, with these types of problems, I like to kind of keep my work divided on the left and right. So, like, this is just what I'm used to doing, and if you don't like it, don't do it. But I like to keep the left side as me integrating. I like to keep the right side of my paper as me trying to rewrite the equation. So that's what this today is all about, rewriting the equation to something I can integrate. So I want to divide, and we have to do long division in this case because we have a coefficient in front of x. I always do square root. I don't know why. All right, so what goes inside is 2x cubed plus 3x squared plus 7x plus 4. So this will be a fun review of what long division looks like. So what are you going to multiply 2x by to give you 2x cubed? That would be x squared. Okay. So then remember we multiplied 2x by x squared and 1 by x squared and line everything up. So 2x squared should give you 2x cubed. Those numbers will always be the same. And then x squared times 1 is just x squared, and we subtract. Okay. 2x cubes cancel, and then 3x squared minus 1x squared is 2x squared. Okay. And you bring the remaining terms down. And then you start the whole process over. So you're going to think, okay, what am I going to multiply 2x by to give me 2x squared? Well, that's going to be just x. And if I multiply that back through, x and 2x is 2x squared. Those should always be the same. And x times 1 is x. So we're going to subtract as usual. Those cancel, and then 7 minus 1x is 6x plus 4. And then lastly, what I need to do is figure out what 2x can multiply into to give me 6x, and that's 3. So 3 times 2x is 6x, and 3 times 1 is 3. So if I subtract that, 6x goes away, and 4 minus 3 is 1. All right. So remember what happens when we have a remainder left over with dividing? You're just going to put that remainder as what's left over, and then you're going to leave it over what we were originally dividing by. So in this case, 2x plus 1. So the thing is whenever I did long division, whenever I actually simplified this fraction out, I am left with this as my value. So this original function is equivalent to the integral of x squared plus x plus 3 plus 1 over 2x plus 1. These two are equivalent. Okay, so that's kind of our first lesson here. It's just using long division to rewrite it as something that I can integrate. And I can integrate this. It's not too terrible. Okay, so for instance, x squared becomes 1/3 x cubed. X is 1/2 x squared. 3 is 3x. And then what about this bad boy? Okay. Well, I want us to get to the point where we don't have to do u substitution with that, but I'm going to anyway, just so you can see it. But if I did like a quick little u sub here, u would be 2x plus 1. du would be 2 dx, so 1/2 du would be dx. So this would end up being 1/2 the integral of 1 over u du. And what is the integration of 1 over u? Well, it's ln of x. So, I mean, this is essentially a 1 over x problem that we're taking the integral of. But just remember that if u is 2x plus 1, all that's going to do is bring a 1/2 out. So my final answer is 1/3 x cubed plus 1/2 x squared plus 3x plus 1/2 ln absolute value of u, or 2x plus 1 plus c. That's it. And that wasn't so terrible, right? I mean, long division to rewrite it, and then we just integrate. Let's try that one. Okie doke. So in this one here, we have a rational, and again, it's a rational that I'm not going to be able to do u sub or anything else with. And this is actually a proper fraction, which means I'm not doing long division. I'm going to be doing partial fractions. Okay, partial fraction decomposition. Now, it's probably been a long time since you've done that, so I want us to kind of refresh ourselves. Again, I'm going to kind of divide the paper in half here. I'm going to do the right side as me rewriting it and splitting it up, and the left side will be the inner. Okay? All right, well, you start by factoring the bottom. So I'm going to start by factoring this to, what would that be, x minus 2 and x minus 5, I believe. So I'm going to rewrite it that way. And the idea is I want to take this fraction, x minus 2, x minus 5, and I want to rewrite it. And I want to rewrite it in its partial fraction. So when I say partial fractions, I had to add two fractions together to get this fraction. And how it breaks apart is you're going to have some number over x minus 5 plus some number over x minus 2. Okay? That's how a partial fraction decomposition works. That's how the fraction splits apart. The goal for us is just to figure out what A and what B are. So again, this is the steps for partial fractions. They split up to where you have one factor under one fraction and another factor under another fraction, with A and B being numbers that we have to solve for. Okay? And that's not a terrible thing to do. All I ever teach students is just to multiply both sides by the common denominator and set up a linear equation and solve. So for instance, like I would multiply this side by x minus 2, x minus 5, and I multiply this side by x minus 2, x minus 5. Okay, now if I distribute the x minus 2 and x minus 5 through, it crosses everything out on this side, so I'm left with 1. If I distribute it through to the a, then the x minus 5's cancel, so I'm left with a and x minus 2. If I multiply it to the b term, the x minus 2's cancel, and I'm left with x minus 5. Okay. Okie doke. Now we got a linear function to solve for. It's actually a pretty simple process to solve for a and b. You just test x values and find the values that make it work. So for instance, like if I'm trying to solve for say for b, I'm gonna let x equal 2. See, watch what happens when I do that. Because of this factor here. If I let x equals 2, then I got 1 equals a times 0 plus b times negative 3. So the a times 0 cancels out, and I'm able to solve for b. So b in this case would equal negative 1/3. So I'm able to solve for b, and I think that's really cool. Like I can do the same thing if I want to solve for a. I can say, what if I let x equal 5? Well, I can use that to solve for a, right? It's going to be 1 equals a times 3 plus 0, and a equals 1/3. Okay. So if I plug these back in, make sure I plug these back in correctly. A, we said was, this is equal to, A was said to be 1/3 over x minus 5. And then plus b, so I guess we'll say minus 1/3 over x minus 2. Okay. But I'm okay with leaving it that way for when we integrate, but just remember that if I have a fraction divided by a fraction, like if I do same change flip, this just ends up being 1 over 3 x minus 5. You can try that simplification on your own. The same change flip is just going to make us have the 1/3 on bottom like that. Okay. So that's what it simplifies to. That's as simple as we're looking at right now for partial fraction decomposition. So this becomes the integral, and this is equal to, like that original problem becomes the integration of 1 over 3 x minus 5 minus 1 over 3 x minus 2 dx. Okay. And this isn't a terrible thing to integrate. We can integrate both of these fractions all day long. I would probably take the 1/3 constant out for each of these. So this will be like 1/3 the integral of 1 over x minus 5. And then minus 1/3 the integration of 1 over x minus 2. And you can do u sub all day, but it's just going to end up being the integration of 1 over u. We can take these integrations pretty simple. It's 1/3 ln, absolute value of x minus 5, and 1/3 ln, absolute value of x minus 2, plus c. So the idea of today's lesson is being able to rewrite rationals as simple as the addition of simpler fractions and integrating each of those components. Okay. All right, I like this next one. Let's try this next one. We got x squared plus 2 over x minus 1, 2x minus 8, and x plus 2. Okay. And it seems to be like, it's already pretty much in factored form, right? 1, 2, 3. I think that's pretty factored. I guess we can make 2x minus 8 as 2 times x minus 4 if we really want to. We can do that. But regardless, we have a higher power on bottom. It's not going to be dividing. This is going to be another partial fraction decomposition. So I'm going to split my paper up here. Okay. And I'm going to do partial fraction decomposition. So I have that x squared plus 2 over my factored form here. That's x minus 1, 2x minus 8, and x plus 2. And because I have 3 unique factors, and the key word there is unique, okay? There are 3 different factors. I'm going to have 3 different fractions that I'm adding together. I'm going to have a over x minus 1 plus b over, and I'll go ahead and say that's 2x minus 4. Why not? Plus c over x plus 2. Okay? Okay, now, I know it's 3 terms instead of 2 terms, but we still do the same process as before. We want to kind of solve for a, b, and c by making this a linear function. So we're going to multiply both sides by the factors, x minus 1, 2x minus 8, x plus 2. And the same thing over here. I'll try to squeeze them in here. X minus 1, 2x minus 8, and x plus 2. I'm sorry that it's squeezed in there, but you get the idea, right? So these all cancel out. I'm left with x squared plus 2 on the left. And then with the a term, I have everything but the x minus 1. So I have the 2, and I'll say x minus 4. I have the, and the other term would be the x plus 2. With the b term, the 2x minus 4, that cancels. I'm left with the x minus 1 and the x plus 2. And for the c term, I cancel out the x plus 2, and I'm left with c, and then x minus 1, and 2x minus 4. Okay. So, like, compared to the last problem, this looks like a lot more because we have 3 terms, 3 unique factors, so it looks a little bit uglier, but it's still solved the same way. Look at your factors. Just plug in x values that crosses those factors out. Like start with, I don't know, start with this x minus 4. What happens if I let x equals 4? Does that cross out some variables? Well, yeah. So like, So, okay, so if I let x equals 4, for instance, okay, if I plug it in on the left side, 4 squared plus 2, that's 18 equals, okay. The 4 is going to cross out your a term, and it's going to cross out your c term. Those are the two factors that have x minus 4. So really, I'm left with the b term. I'm left with b, 4 minus 1 is 3, 4 plus 2 is 6. So that's what I'm left with. 3 times 6 is 18, so b equals 1. All right, like find another factor. Like what happens if, for instance, I let, I don't know, let's let x equal 1. That's another factor. Well, that's going to cross off your b term and your c term. Those are the ones that have x minus 1. So that's going to be 1 squared plus 2, so I have 3 equals a, and then that's 2 times 1 minus 4 is 3, negative 3, and then 1 plus 2 is 3. So that's 3 equals a times, that was that, negative 18. So now a equals 3 over negative 18, or negative 1/6. Okay. And then lastly, okay, so we, let's see, we plugged in 4, plugged in 1. Is there another factor I can plug a number into? How about, yeah, how about negative 2? What if I let x equals negative 2? I can solve for another variable. So what if I let x equal negative 2? Well, the good thing is that's going to cross out a term, that's going to cross out your b term, and I'm going to end up being able to solve for c. So negative 2 squared plus 4 is 6 equals c, and then it's 1, or negative 2 minus 1 is negative 3. And then I got 2, and then x minus 4, or negative 2 minus 4 is negative 6. Okay. And I can solve for c. So what's that? Negative 12, or positive 36. So I got c times 36 equals 6, or c equals 1/6. Okay. So we got my a term, we got my b term, we got my c term. Let's plug those bad boys back into the original. We'll integrate. So this integration is equivalent to the integration of, instead of a over x minus 1, it's going to be negative 1/6 x minus 1. Instead of b, we're going to have 1 over 2 x minus 4. And instead of c, we're going to have 1/6. So we're going to have 1 over 6 x plus 2. So this situation right here, if I were to combine these like terms, I'd be back to where I started. So all I did was just rip the fraction apart. Now, I can integrate it the same way before. I would take your constants out. Like I would take out the negative 1/6. I would take out the 1/2. And I'd take out the 1/6. But I'm sure you're noticing a pattern here. Again, it's just 1 over x, 1 over x, 1 over x. The integral is going to be ln. So I got negative 1/6 ln absolute value x minus 1. I got 1/2 ln absolute value of x minus 4. And I got 1/6 ln absolute value of x plus 2. Plus c, don't forget the plus c for us. So the goal today is to rewrite our rationals to smaller fractions. All right, I think I got time to do maybe one more. Okay, this will be my last one, and then I'll say the last few problems for in class. We've got some unique problems we're going to try. So maybe pause the video, maybe try this one on your own, but it's pretty similar to the other ones we're doing. Okay, so you know, identify that we have a rational here that we can't integrate with any of the property. It's rational. The higher degree is on bottom, so it's proper. So we're going to do partial fractions. Okay, so split up my paper. And I'm going to rewrite it. Now I'm going to rewrite it doing partial fractions. And this is especially true if I can factor the bottom. Like I can factor the bottom to x times x squared minus 1, or x minus 1, x plus 1. Like that's what the factor breaks down to. So that means whenever I do this bad boy, I'm going to have x squared plus 2x minus 1 over x minus 1, x plus 1, equal to 3 fractions, because I have 3 unique, keyword unique, factors. So I'm going to have a over x plus b over x minus 1 plus c over x plus 1. And I'm not gonna write. I mean, we multiply both sides by all the factors. Okay, I'm not gonna rewrite that step again. But just remember that on the left side they all cancel out, and I'm just left with the top. On the right side with the a term, everything the x cancels, and I'm left with everything else. With the b term, the x minus 1 cancels, so I'm left with x and x plus 1. And with the c term, the x plus 1 cancels, so I'm left with x and x minus 1. Okay. So I'm sure you already know where this is going. Partial fraction decomposition is not the worst thing in the world. We're just going to try to solve for a, b, and c, and the easiest way to do that is to plug in values for x to cancel out other terms. So let's start off with the easy one. Let's start off, well, they're all pretty straightforward. Let's just let x equal 1. Okay? Well, I plug 1 into the left side, I think I get, I'm getting 2 equals, the a term crosses out and the c term crosses out. So I'm left with b times 1 plus 1 is 2. So in this case, b equals 1. What's the other x value I can do? How about, instead of 1, how about negative 1? All right, so if I plug that in on the left side, I'm actually getting negative 2. And then negative 1 crosses out the a term and the b term, so I'm left with c times negative 1 times negative 2. Which in this case would just make c equal to negative 1. What's my last one I can do? What if I let x equal maybe 0? Okay, so on the left side I have negative 1. On the right side, my b term and my c term go away, and I'm left with a times negative 1 times positive 1. So a equals 1. Okay. So I got what a, b, and c are, and those are the worst numbers in the world to deal with. A and b are 1, and c is negative 1. So I can go ahead and write the equivalent integral, what this splits up to be. So a was equal to positive 1, so instead of a over x, it's 1 over x. B was equal to 1, so instead of b over x minus 1, it's b over, or 1 over x minus 1. And c was negative 1, so that's minus 1 over x plus 1 dx. So there you have it. I mean, this integral can be rewritten as that integral. And again, you notice the pattern here. These are all ln's, so that's ln absolute value of x plus ln absolute value x minus 1 minus ln absolute value of x plus 1 plus c. All right. So there you go. So not the worst thing in the world. Partial fraction decomposition just takes practice. And we're going to do plenty of more. I got about 4 or 5 more problems I'm going to do in class that are some unique stuff. So we'll just pick it back up with that tomorrow. So good job, guys, and I hope y'all have the best of days. And I will talk to y'all soon.